try to embed the U1 gauge field as the geometry by uplift the solution to the 5 dimension. Okay. Because in the 5 dimension, Karusa-Klein vector just like the gauge field in the 4 dimension. So we can uplift the solution into the 5 dimension. Okay. And then if we in the 5 dimension, the ADS2, this ADS2 plus the gauge no, because uplift the gauge field part is already be included in the part of the extra dimension, and then that part combined as the warp ADS3. Okay, but in this case there's some ambiguity or uncertainties because we embedded in the higher dimension. So we have the question: what's the size of the extra dimension? And this is actually related to how the relation between the 4-dimensional gravitational constant and the 5-dimensional gravitational constant. So that's some kind of parameter. Okay, is undetermined. But nevertheless, we can have a warp ADS3 and we can repeat the same calculation what we did for the curved black hole, and then we can also compute the central charge of the CFT and also the temperature. Okay. And again, the entropy produced by the conformal field theory is exactly the same as the entropy of the Larsen-Norton black hole or charged black hole. So this is for the charged black hole case. Okay, but in general, the black hole has more than two parameters. Just has, so we consider most of the general case just Kerr-Newman black hole. So Kerr-Newman black hole can have angular momentum and can also have charge. So they can have two choice of the ADS3 structure. One is just the combine with the angular momentum part. Okay. So this is the from the geometry. Okay. We present the angular momentum. And it also can be combined with the gauge field. So there are two possible ADS3 structure can be obtained in the Kerr-Newman black hole. And with detail and that also repeat the mechanism. So we can have two CFT description of the Kerr-Newman. So because this is the angular momentum description, so we call this the J picture. And this is the charge distribution. We call this Q picture. So we can have two equivalent CFT with different central charge and the temperature, but they both can reproduce the entropy of the Kerr-Newman black hole. And the case is similar for each hair of the black hole, in addition to the mass. Okay, because the mass, because okay, we can imagine this because our example always focus on the extremo, and the extremo means we put a certain condition for the mass. Okay, so this means the mass in the extremo limit, the mass already not a free parameter. Okay, is determined by the charge or by the angular momentum or forces. So the independent parameter there are only two: angular momentum, independent parameter only angular momentum and the charge. And these two physical parameter or physical hair, each one give us the CFT description. Okay, we can have two. So if we can generalize to higher dimension of black hole, and this also test in the higher dimension of black hole, we can have more angular momentum, and also we can carry more than one charge. For example, the magnetic charge, and we can have each angular momentum, each charge parameter can give us the CFT description. So this is the quick summary about the black hole CFT on the three well-known black hole for in the general relativity.
Actually, what is the physical picture of this hair? Because earlier, okay.
Because hair means that
we don't have it, right? No hair. So now we have.
So actually, no hair is the name, but actually, this is what maybe I actually the black hole can have three. 3 hair, just the mass, charge, and electron momentum. In the English name, it's called no
the
hair.
physical picture, they're not look like hair. Okay, they just extra, quantitative, some quantum number.
Yeah, so this is just a
Cartoon. I know it's a cartoon. But still, okay, you use hair. Okay.
Just the black hole can only have three
extras.
parameters. Okay. So if the black hole has the same mass, for example, then without charge, there's only one solution. Not just like I have same mass, but the mass can have different distribution. I can construct different configuration. But for black hole, it's simple. If the mass is the same, the solution is unique.
No, you should try to use the physical picture, like our sun.
Yeah.
Okay, sun had those, right? Those, the black spots. They can have hairs, easily. Okay.
Yeah.
But here, I don't know. That's why I asked. Okay, when you use hair, what does that mean?
Yeah. But here, so yeah, here hair is just like the parameter for the black hole. But actually there are 3 parameters, but English they call this no hair, no additional.
3 parameters. But generally, there should be 1 hair, right? If you use that, the mass has to be there.
But yeah, because you need the horizon. You need the gravitational force, and the mass is the main source of the gravitational force. So the mass is always should be
there. So it's 1 hair.
But 3 hairs, I mean, mostly we can have 3. But yeah.
No.
Yeah. Okay. Yeah.
You have a no hair theorem.
Yeah, but no hair is I don't know why. The history why they call it no hair.
It should be called 3 hair here.
Yeah. Much more than 3 hair. So it's more.
So can a black hole also carries magnetic dipole or electric dipole?
But it means the charge is equal to 0, but the dipole moment.
They may be separated internally.
Yeah, but such kind of you can have the two.
According to the theory, it's not enough.
Right, it's not stable.
Yeah, because they have some additional. If you have
But with the spin, maybe it's stable.
Yeah.
And the theorem tells you.
Okay.
Yeah. So what?
About the dipole. He said dipole is not stable.
Yeah, because in the dipole you need to have two singularity.
Yeah.
Or if the charge is uniformly distributed and it's rotating, then you could have a magnetic dipole.
If the charge is because in this for example in this case the charge and the mass is of course from the mathematical structure of the solution the mass and source is located at just the singularity.
I know, but
also if you have dipole you should have 2.
No, but we have dipole, right? Electrons.
Yeah, but they are not form of black hole. Yeah, if you want to
Doesn't
form a
matter.
black hole,
It's pointless. We say point particle. There's no dimension to it. In general, right? It has spin, has a mass, then it has dipole. So in principle, you can apply to here too.
yeah, but then you should compute what's the spatial radius of this.
It's tiny.
Like
It's tiny, but still can be calculated, right?
yeah, but the spatial radius of the electron should be much smaller than maybe it's the size of the electron, because size of the electron is already not.
I agree. So now the question is, where does this dipole comes from electron? We call it from the Dirac equation, right?
Yeah.
How does it come out? If you follow the the black hole theorem here, somehow it has to come out. It's outside the black hole.
Yeah, but if the charge distribution does not form a black hole, of course the charge can. Yeah, just like maybe not just like a mass. For example, the mass my body, I have a certain mass,
Yeah.
but I did not form a black hole. So my configuration is there are many different kind of this is one configuration is one, but once my mass swings to become a black hole, then
So for this pictures, maybe the inside the electron do have this micro black hole, then it has a spin, it spins. Then change the distribution outside, the charge distribution outside the electrons, and makes the dipole. If you want to use that picture, right? Well, right now, we have equation like direct equation, but we cannot explain it.
Yeah.
Now, the black hole, in principle, is try to explain those things. Black hole in the string.
Yeah.
So I would like to find some connections.
Yeah.
You mean like electron as a small black hole?
Everything has a black hole, right? According to the string theory, everything has inner dimension. It has to have a micro black hole.
Not necessarily, but anyway, so that would be a quantum theory. This is a classical gravity theorem. So we believe that it's violated at quantum level. So in string theory, we believe this is not true. No hair theorem is not true.
So you consider quantum.
All right.
Yeah, okay, so this is the so the next I want to talk another result about to discuss the simultaneous pair production. So our motivation is try to understand this small object. One purpose is to analyze this, and the other one purpose is try to see how the holographic picture to interpret this kind of simultaneous pair production. So what is simultaneous pair production? We consider the quantum fluctuation, vacuum fluctuation, and produce a lot of the virtual particle. And so if we have some particular mechanism can transform this virtual particle to real particle. So there are two possible ways. One is to use the electric field. So if this the virtual particle can be charged, and if we can apply the electric field, and we can get the pair production. And then the other one is because of the causal horizon, and because in the causal horizon there's a quantum tunneling near the horizon, and can also possible to produce the real particle. Okay, so this is the original mechanism for the Hawking radiation. But because of course this kind of topic people already investigate a lot, analysis the simultaneous pair production. But we want to consider the pair production in terms of the holographic duality. Okay. So we have two criteria to choose our background for analysis. One is we want to the system is simple, technical simple. We can solve the system by hand. Okay. And what I learned from the people working on this area, they say we should start to choose what the constant electric field for the Schwinger mechanism, because if the electric field is not constant, then the Schwinger mechanism becomes complicated to be solved. And from the holographic point of view, we want to have the system in the entity space, because the holographic is more or less known in the entity case, not in general. So we try to choose a particular background and can satisfy these two requirements. And it's turned out the Western Northern black hole and in the near extremum case is really to provide such kind of the background. And remember, I just said in the near Horan geometry of the Western Northern we have ADS2 cross S2 structure, okay, and plus the gauge field, and then we check the gauge field. This is actually has the constant electrical field, so the electrical field is constant in this system, and also we have ADS2 cross S2. And in addition, some of the CFT information we already know from the previous analysis. For example, the central charge and the temperature, etc. Okay. So this is the good background for try, and we start to compute the pair production, and then try to understand this pair production in the quantum field theory side, conformal field theory side. Okay. And here is some remarks. In the extreme, so we start from the extreme case. The extreme black hole, that means outer horizon and inner horizon are degenerate. And in this case, the Hawking temperature is equal to 0. Okay. So from the thermodynamical point of view, this is stable, okay, because there is no thermal radiation. But there is the constant electrical field. So electric field is not vanished. And this means they can produce the Swinger, they can produce the particle due to the Swinger mechanism. Okay. So this means even the extreme black hole thermodynamically stable, they can still have the here particle production. Okay. And then from the gravity point of view, there's another interesting question to ask is because we want to have the cosmic censorship. Suggesting the negative singularity does not exist in the physical system to protect the existence of the negative singularity. So then when we discuss this, we also are interested to ask if we have an extreme black hole, okay, and after the pair production, this can produce the negative singularity or not, okay. And such kind of question also we also can answer this in this kind of analysis. Okay, so now I want for this part go into more a little more technical detail on this. Okay, so we want to consider the Near-Horizon geometry of the Northern black hole. So if we draw the coordinate of the Northern black hole, so this is time coordinate and this is radial coordinate, and just ignore the angular coordinate. So in general, there are two horizons. We call the outer horizon and the inner horizon. And the extreme limiter means the inner horizon is degenerated with the outer horizon. Okay. So R plus is approach to the R minus. And we will only focus on the near horizon geometry. Okay. So this means we run out this small region, okay, to the space-time, to the whole space-time, and then try to analyze the near horizon geometry, the pair production in this near horizon geometry. And the physical reason for this is because we expect the pair production generated by the black holes appear in the near horizon. Okay, so for the iron black hole, this is the formula for the inner and outer horizon. So charge black hole can carry mass parameter and charge parameter. Okay. And then from these two parameters, we can find the location of the two horizons. Okay. So from this formula, we know if mass equal to charge, then the two horizons degenerate. And we just try to analyze pair production in this near horizon geometry, and then to try to see what is the production rate, some information about the pair production, and then how to compute the particle creation. Okay. And then in this work we only consider the simple case. We consider the production of the charge scalar field. So it's a massive charge. So it's charge scalar field. Okay. And then we try to analysis is consider the propagating mode of the charge scalar field and impose certain boundary condition. Okay. So this is location on the boundary, and this is is the horizon. Okay. This is the near horizon, and this is the near the outer horizon asymptotic. And what the boundary imposed? Okay, because the horizon of black hole is located here. So we just the pair production is at the infinity at the outside the black hole, and we see how many we see the particle creation or particle or the flux move to the outside the horizon without anything moving in. Okay. So we impose the boundary condition that the inward flux is equal to 0, and try to see how much outward flux. Okay. And this flux is coming from the this flux is due to the flux on this side. Okay. So we try to find the solution of the scalar field and impose this boundary condition. Okay.
So the vertical scale it's like
it's just like a,
or what?
This is just like a means the what?
What's a vertical scale? Because you have a curve.
Oh, this
so that's a
vertical.
scalar field, right?
Yeah, this is just like a input. I have a scalar field propagate on the space. This is space, and this is the potential, like the effective potential is the scalar field.
So then, what is the vertical scale? Oh, vertical axis.
So this is just schematic. This is just potential seen by the scalar field. Yeah. Effective of course, the effective potential set another way is more complicated, but this is just the schematic.
So why is outside? It's not inside.
It means what here?
This curve, this potential. Why this potential is outside? It's not inside. The rho equals 0 is the inner boundary of horizon.
Yeah, rho equal to.
Then you have a rho equal to infinity.
Yeah, but so remember this rho from the 0 to infinity is this region in the black hole. So it's just near the horizon of the black hole.
Oh, okay. So I misunderstood.
So this
I thought rho equals 0. So rho equals 0 is 0. It's not
no, rho equal to 0 is almost just like near on the horizon.
So that's still my question. Why that scalar field is not inside? It's outside.
Well, because we stand outside the horizon to see what's the particle come out. Yeah.
Okay. So you could have a solution.
And we try to find a solution of the solution outside the horizon.
I see.
Yeah. Okay, and then so outside the horizon, we sit here. Okay, more far away from the horizon and see how much particle produced, and we do not put anything in, but we shoot the particle out.
I understand your condition. Yeah. That's why I understand the picture.
Yeah.
So
and how this particle created? This is created something happen near the horizon.
Yeah. So you can actually also discuss something inside, if you actually throw things from the outside. Right?
It means, yeah. Yeah. But this, okay, maybe I can continue. I'm not sure. But this is my interpretation. This is the boundary condition we impose from the particle point of view.
Mm.
So this is so the interpretation. This is the pair production of the virtual particle, and the reflected. This is the reannihilation part, and only this part becomes the real particle. So and then this is the incident part is the virtual particle created by quantum fluctuation, and the reflected part is the reannihilated part, and then transmitted part is just the pair produced particle. And then we need to so from this we can try to see how the production rate by compare with the ratio of this flux. But this also can be impose another boundary condition. We can impose the equivalently we can impose this another boundary condition. This is equal to 0. Okay. So but this we should interpret interpreted is the view from the antiparticle. Okay. So the particle produced the wave from escape from the black hole is equivalent to some antiparticle move inside the black hole. Because the pair production, so if the pair virtual particle becomes the real, the particle moves to the outside, and the antiparticle fall into the black hole. So this is another picture. Okay. So in this case, this is the virtual particle. This is the realization, and this is the antiparticle fall into the black hole. We can impose this kind of boundary condition, and this can be checked. Okay, the flux ratio computed by this boundary condition and another boundary condition, they are equivalent. Okay, so then what's the quantity we compute? The quantity computed actually is the ratio of the flux. Okay. For example, we can compute the alpha squared. Alpha squared is defined as the incident part and the ratio with the reflected part. But remember, the reflected part is the reannihilation, and this is the virtual part. This is the virtual particle. So more physical, more easy to understand, you can consider 1 over r squared. 1 over r squared is the reflected part ratio with the incident part. So this means if the 1 over alpha squared is bigger, then this means less the real particle will be produced. Because if this is equal to 1, so all the virtual particle will annihilate. So no any particle creation. So 1 over alpha squared is called a vacuum persistence. But historically, this part, when I check another paper, people call this alpha squared the vacuum persistent amplitude. But physically, it should be the value should be 1 over alpha squared. But why you use alpha? Because the alpha and the beta they are mapped with the Bogoliubov coefficient. So people, it's more convenient to use alpha squared. But physical interpretation should be 1 over alpha squared, the vacuum persistence. But in the literature, people call this alpha squared, also called the vacuum persistence. Yeah.
So alpha should be related to the potential, right? The charge scalar potential.
Yeah, of course, it depends on the dynamics of the. Yeah.
So if I give you a square.
Yeah, so it depends on the
square potential. They should be.
Yeah, it depends on the solution. Depends on the solution here. But I want to compute this system with the boundary in the background. Okay, and another parameter you can choose is the transmit compared with the reflected. So this is the reannihilation, and this is the produced. Okay, and then people call this the mean number of production pair. And also we can compute the association cross section, just how many. So this is how many particle create compared with the total virtual creation. Okay. Of course, they are not independent. They are related to each other. Okay. So this is the quantity we try to compute, and then the physical meaning of each parameter here.
So you assume nothing lost.
Yeah. So the flux should conserve the instant should be.
But what happens if that scalar field actually do absorb stuff?
Do absorb during the. Yeah, but here I only have the space-time background and the one scalar field, and this scalar. Okay. So here I also the scalar field is just like a Prof scalar field. Yeah, maybe this is the. Okay, here actually. When I consider this, I neglect the back reaction. I mean the background provide the gravitational back reaction